At 09:50:45 UTC on September 14, 2015, two LIGO observatories recorded GW14914, and it is tempting to say that Einstein had just passed a test. But the event did not test Einstein alone. It tested a whole arrangement of theories, instruments, calculations, and judgments about what counted as a signal. LIGO announced GW1509114 on February 11, 2016, as the first direct detection of gravitational waves. The signal had appeared at both observatories, Hanford, Washington, and Livingston, Louisiana. In 2016, the LIGO Scientific Collaboration and Virgo Collaboration published the discovery paper in Physical Review Letters. Its interpretation was specific. GW15091 was presented as a binary black hole merger. That interpretation had an extraordinary force. A signal arrived in two distant instruments. Its form was analyzed. It was connected to a prediction from general relativity. The results seemed to establish a direct line from Einstein's theory to the physical universe. But that line was never direct in the simple sense. The phrase "Einstein was tested" compresses a great many things into one sentence. It compresses the theory of gravitational waves. It compresses an account of black holes and their merger. It compresses the operation of lasers and interferometers. It compresses the calibration that turns raw detector output into a physical estimate. It compresses the procedures used to distinguish an astrophysical event from a disturbance inside a detector. None of this makes the detection weak. It makes the achievement more exacting. The claim did not emerge because one equation met one observation in isolation. It emerged because many linked claims held together across two observatories, a shared analysis, and a carefully constructed interpretation. This matters because the usual image of scientific testing is too clean. We imagine a theory standing before nature like a defendant, before a judge. Nature delivers a verdict, confirmed or refuted, but the actual situation is more crowded. The theory comes to the test with equipment, background assumptions, models of the source, and procedures for deciding what the equipment has recorded. GW15094 therefore gives us a concrete philosophical problem. If the evidence depends on such a network, what exactly does an experiment test when it seems to test Einstein? Pierre Duhem had already formulated the core of that problem long before LIGO existed. Duhem was a French physicist and philosopher who lived from 1861 to 1916. In The Aim and Structure of Physical Theory, published in 1906, he argued that a physical experiment does not test one hypothesis by itself. It tests a connected set of hypotheses. This position is often called confirmation holism. Observational results depend on theory, auxiliary assumptions, and measurement practices together. An auxiliary assumption is a supporting claim required to connect a theory with an observation. A measurement practice is the procedure by which an instrument's output becomes evidence. Duhem's point is not that experiments are useless. It is more demanding than that. An experiment can place a whole system under pressure. It can reveal that something in the system does not fit. But when prediction and observation diverge, the failure does not mechanically identify the guilty member. Suppose an expected result fails to appear. Perhaps the central theory is wrong, but perhaps the supporting model was mistaken. Perhaps an assumption about the instrument was mistaken. Perhaps the procedure for interpreting its output was mistaken. The observation tells us that the connected set has a problem. It does not, by itself, tell us whether repair must be made. That is the Duhem problem in its sharp form. There is no pure confrontation between a single theory and a bare fact, because facts in physics are reached through organized practices of measurement and interpretation. Applied to GW1509114, this sounds almost obvious. LIGO did not simply look at space-time and read off a message saying, "General relativity confirmed." It recorded output from an interferometer. That output needed calibration. It needed comparison between sites. It needed analysis against possible non-astrophysical disturbances. It needed to be interpreted through a model of a binary black hole merger. The strongest objection to this argument has a name, and it will matter later. Karl Popper warns that this flexibility can become a way of protecting any theory from any evidence. We will have to ask whether Duhem's insight explains scientific rigor or dissolves it. Before that objection can land, we need to see how Einstein's prediction became something LIGO could actually measure. Albert Einstein presented the field equations of general relativity in 1915. In 1916, he published a paper on gravitational waves. General relativity predicts that accelerating masses can generate ripples in space-time called gravitational waves. That claim is already conceptually difficult. A gravitational wave is not an object that an instrument simply collects. It is a predicted effect described within general relativity. To detect it, LIGO measures changes in the relative lengths of two perpendicular arms using laser interferometry. Interferometry is a method that uses laser light to detect tiny differences in path length. Each LIGO observatory has two arms approximately 4 kilometers long. A gravitational wave signal is not identified by one arm, changing in isolation. The relevant measurement concerns the relative change between the perpendicular arms. The instrument is designed so that this relation can be inferred from its laser-based output. Now the structure of Duhem's argument becomes visible inside the apparatus itself. General relativity supplies a prediction about gravitational waves, but the prediction becomes testable only when joined to an account of how a gravitational wave would affect relative arm lengths. That account becomes measurable only through laser interferometry, and the interferometer's output becomes evidence only through further assumptions about what the output represents. The theory is not being hidden behind the instrument. It is being given a route to observation. That route is necessary. Without it, gravitational waves exist would remain a theoretical statement with no specified experimental handle. The same is true of the binary black hole interpretation. The 2016 discovery paper did not merely state that LIGO had registered an unexplained pattern. It interpreted GBAB 0914 as a binary black hole merger. That conclusion connected the observed signal to detailed physical modeling. The event was meaningful because its signal could be placed within a structured account of what had happened. This is why it is misleading to treat the instrumental side as mere background. The detector does not sit outside the theory, passively delivering uninterpreted facts, nor does theory float above the detector, untouched by the practical conditions of measurement. The two meet through a chain of claims, each of which has to work well enough for the final interpretation to be credible. But there is a problem with this argument. If the measurement chain is essential, then the credibility of GW 0914 depends not only on the predicted waveform, but on whether LIGO could establish that its own output was trustworthy. That problem brings us from the broad philosophy of testing to the labor of calibration and error control. LIGO calibration converts the interferometer's raw output into an estimate of gravitational wave strain. Strain is the fractional change in arm length. This conversion is not a decorative technical step. Without it, there is raw output from an instrument, but not yet an estimate expressed as gravitational wave strain. The scientific claim depends on the connection between those two things. LIGO uses photon calibrators to help calibrate its detectors. Photon calibrators are auxiliary lasers whose radiation pressure moves test masses by known amounts. The phrase known amounts matters. Calibration requires a controlled relation between a deliberately produced effect and the detector's response. Only through such procedures can raw output be connected to an estimate of physical strain. Then there are glitches. A glitch is a short non-astrophysical detector disturbance. The existence of glitches mean that not every unusual feature in the data is evidence of an event beyond the observatory. A signal has to be considered against the possibility that it came from the detector rather than from the astrophysical source proposed in the interpretation. The two observatory structure mattered here as well. GW 0914 was observed at Hanford and Livingston. In the analysis, LIGO estimated false alarm rates by comparing time-shifted data streams from the separated observatories. A false alarm rate is an estimate of how often an apparent event could arise without the proposed astrophysical explanation. Time shifts do not magically remove every uncertainty. They do something more disciplined. They help establish a background against which the coincident signal can be assessed. The analysis thereby connects the observed event to an estimate of how unusual it would be under the relevant comparison. This is Duhem's point made concrete. Calibration, photon calibrators, glitches, time-shifted streams, and false alarm estimates are not embarrassing additions to a supposedly pure test. They are part of what turns an instrumental occurrence into evidence. Still, Duhem's position now faces its most serious danger. If a mismatch can always be assigned to calibration, background estimation, a source model, or some other supporting assumption, then researchers may be able to save a favored theory indefinitely. Karl Popper formulated this danger with unusual force. In The Logic of Scientific Discovery, first published in German in 1934, Popper argued that scientific theories should make claims that risk refutation. A theory is scientific on this view, not because it can be made compatible with anything, but because it exposes itself to possible failure. Popper's strongest objection to Duhem-style flexibility is that researchers can protect any theory from evidence by adding ad hoc auxiliary assumptions. An ad hoc assumption is an adjustment introduced simply to avoid a threatening result. If every failure can be explained away by changing some supporting claim, then no result can count against the central theory. The theory becomes insulated rather than tested. This is a serious objection, not a rhetorical one. It identifies a real temptation in scientific reasoning. When a result conflicts with expectation, there is always pressure to blame the instrument, the analysis, the background, or some imperfectly specified condition. Sometimes that is exactly right, but it cannot be the answer by default. Duhem tells us that evidence underdetermines the location of an error. Underdetermination means that the result alone does not uniquely dictate which assumption must be changed. Popper adds that this fact can be abused. A research community can turn legitimate caution into a system for avoiding defeat. Imre Lakatos offered a way to distinguish productive revision from mere evasion. In Falsification and the Methodology of Scientific Research Programs, published in 1970, Lakatos distinguished a program's hardcore from its revisable protective belt. The hardcore is the program's central commitments. The protective belt is the surrounding set of revisable supporting assumptions. Lakatos did not deny that scientific work revises its supporting claims. He made that ordinary fact central. Instruments can be improved, models can be adjusted, methods of analysis can be developed. The question is not whether a research program changes. The question is what its changes accomplish. For Lakatos, revisions are scientifically productive when they lead to novel, successful predictions, rather than merely accommodating known failures. This gives us a standard sharper than simple stubbornness, and more realistic than the fantasy of testing one isolated proposition. A program may revise its protective belt without becoming irrational, provided those revisions expand its successful reach, rather than only shielding it from trouble already encountered. The LIGO case, therefore, does not show that anything can be saved. It shows that a claim earns credibility through a system that can be scrutinized at multiple points: the detector's calibration, the treatment of glitches, the estimation of false alarms, the agreement between separated observatories, and the interpretation of the event. But a final case raises the standard further. Can independent forms of observation strengthen this web without turning it into the test of one proposition alone? On August 17, 2017, LIGO and Virgo detected GW10817, a gravitational wave signal from a binary neutron star merger. Shortly after the gravitational wave event, the Fermi Gamma-ray Space Telescope detected an associated short gamma-ray burst. GW10817 became a multi-messenger observation. Multi-messenger observations combine gravitational wave data with electromagnetic observations from many telescopes. The result was not simply one instrument repeating another. Different instruments contributed different forms of observation. The gravitational wave signal and electromagnetic observations were coordinated around the same event. This is a powerful answer to the fear that Duhem makes evidence arbitrary. Duhem does not say that every interpretation is equally good. He says that scientific confidence is built by testing and coordinating many linked claims. GW10817 displays that structure with unusual clarity. Gravitational wave data were not left alone. They were placed in relation with electromagnetic observations, including the gamma-ray burst detected shortly after the event. The evidence remains a web. It does not become a single proposition tested against a single fact, but the web can become stronger when its strands are independently structured and can be brought into coordination around a shared event. That is the modern stake of Duhem's insight. Einstein was not tested alone in 2015, and gravitational wave science did not become less rigorous for that reason. Its rigor consisted in making the dependencies visible enough to calibrate, monitor, compare, estimate, revise, and coordinate. The remaining question is how much independent convergence a scientific web needs before we are entitled to treat its central claims as secure. Subscribe for more careful arguments about science and philosophy.